Hi, and welcome to our section on networking, microservices, and asynchronous programming. In this section, we're going to be looking at Python's built-in Async IO framework and the AIO HTTP, asynchronous HTTP library built on top of it, as our software of choice for writing asynchronous IO-bound programs. Microservices are a prime example of this kind of software, and we'll learn the fundamentals of writing a microservice in Python based on these libraries. We'll also take time to look at how to combine Async IO and ReactiveX in the same program. Finally, we'll write a server for our ORE game. We'll start by talking about Async IO and coroutines. Before we get into the details, we're going to talk about what IOBound means, and why it's a consideration when we're deciding how to structure our programs. After that, we'll look at what Async IO is and what it does, and from there we'll talk about what coroutines are and why we use them in conjunction with Async IO. Finally, we'll write a simple Async IO and coroutine-based program to see it all in action. Software does not run with infinite speed, so there's always some limit on it that is preventing it from running faster. If that limit is simply that our computer is running full out and can't possibly do more computations per second, we say that the program is processor bound. On the other hand, if the program is spending time waiting for input, we say it is IO bound. Even if the processor was faster, the program would still be waiting for input, and so it wouldn't run any faster. It's a less common situation, but outputting results also takes time, and in some cases is the limiting factor. This is another version of being IO bound. The I stands for input, and the O stands for output. If a program is processor bound, speeding it up requires that we use either a faster processor, or more of them. We have a section devoted to that later in the course. However, most programs are IO bound, including network servers. They spend more time waiting than anything else. In many cases, servers in particular, our program could be doing something useful while it waits for input. After all, servers often interact with several clients at the same time, and so it could be doing something useful for one client, at the same time that it's waiting for another. The simple way to allow for that possibility has been to use a thread for each connected client, so that waiting for input in one thread does not prevent other threads from doing anything they might need to do. That works, but time has shown it to be inefficient. The problem is that threads have a pretty high overhead. There are only so many threads a server can run before getting bogged down by the memory requirements, or exhausting the operating system's available thread handles, or so on. Another way to allow a program to keep performing useful tasks while it waits for input is to use asynchronous IO. With asynchronous IO, instead of waiting for input, we periodically check whether input is available. If it is, we process it, and if it's not, we go about our other business. This allows a single-threaded program to handle many more simultaneous tasks than a multi-threaded program, as long as the tasks are IO-bound. We used a very primitive version of asynchronous IO in our ORE client in the last section, by setting the socket to non-blocking mode. There are much better low-level ways to handle polling input sources to see if input is possible, but they still end up being easy to get wrong, and programs built around them are structured in ways that make them harder to read, comprehend, and edit. So, for IO-bound programs, asynchronous IO provides us with the ability to do more using fewer resources, but using multi-threading allows us to structure our program in a way that is easier to work with. That looks like a dilemma, but fortunately Async IO gives us a third choice. We can have the efficiency of an asynchronous IO program while structuring our software in a way that resembles multi-threading. To do this, Async IO runs a scheduler as the program's main loop. This scheduler keeps track of input and output operations using asynchronous mechanisms, but it also keeps track of thread-like objects called tasks. A task consists of one or more coroutines, which are like Python's normal functions, with the big difference that they can be suspended and resumed under the control of the scheduler. You can spot coroutines because they use the async and await keywords, which are syntax errors outside of coroutines. I said tasks are thread-like, not that they are threads, because there are some important differences. First of all, tasks don't use up operating system handles, or most of the other resources that limit the number of threads we can have running. They do use memory, of course, and in the end that puts a limit on how many tasks we can have, but it's a much looser limit. Second, tasks use what is called cooperative scheduling, where threads use preemptive scheduling. That means that tasks can only be suspended at specific points during their execution, while threads can be suspended at any point. There are advantages and disadvantages to both approaches, but cooperative scheduling means that synchronization errors between tasks are significantly less of a problem, and again, has less overhead than preemptive scheduling. The main downside of cooperative scheduling is that if a task doesn't provide any suspend points within the body of a loop, the scheduler will not be able to suspend it until the loop is done, which can result in non-responsive periods for the program. That's less of a problem than it may seem, because the place where coroutines can be suspended is when they use an await expression, and most long-running loops in coroutines naturally call other coroutines at some point, which uses the await expression. For those that don't, inserting a call to async IO.sleep in the loop body will allow other tasks to run. By the same token, that means that sequences of instructions between await expressions are atomic, meaning that we never have to worry about what happens if the task is suspended halfway through them. Okay, enough theory. Let's build a program using async IO and coroutines. Here we have a basic async IO program demonstrating coroutine scheduling. We're not actually doing any asynchronous IO here, but we'll get to that soon. What we are doing is running 3 tasks within the async IO scheduler. Starting from the bottom of the program, we have a call to async IO.run to schedule our main task for execution and run the async IO main loop. Our main task's entry point is the coroutine named main, which we can recognize as a coroutine because it is defined by async def. Our main coroutine calls the normal print function, and then calls async IO.createTask twice to launch 2 more tasks. After those 2 calls to create task are complete, the async IO scheduler has 3 tasks to run, and none of them are yet complete. The main coroutine then uses the await expression to wait for both of the tasks it launched to complete, and then prints out another message before ending. When the main task ends, the async IO main loop also ends, and the program terminates. The delay print coroutine is used as the entry point for the 2 tasks that the main coroutine launched. It simply calls the async IO.sleep coroutine to delay itself for a random length of time, and then prints out the return value from sleep, which will be the value we passed as a parameter to delay print, since we used it as the sleep's result parameter. So what exactly does the await keyword do? It kind of looks like we're using it to do different things in different parts of this program. We're not, though. Fundamentally, an await expression suspends the current coroutine until the scheduler tells it to resume. To await, we have to provide it what's called an awaitable value. Primarily, that means coroutines, tasks, and something we haven't seen yet called a future. Each of them represents something that will happen eventually, but hasn't happened yet. A called coroutine will in time produce a return value, for example. An await expression tells the scheduler to wait until that time has come before scheduling the current coroutine to continue running. Await expressions also conveniently produce the value we were waiting for as their result. We can see that happening in delay print, where we awaited a call to async IO.sleep to provide the value for printing. Something else to notice is that we pass the return value from actually calling the coroutine as the parameter to async IO.run, async IO.createTask, and await. When we call a coroutine, the instructions in the coroutine do not get immediately executed, as they would with a normal function. Instead, a coroutine object is immediately returned. A coroutine object provides us with the way to control the execution of the code in the coroutine, allowing us to decide when and how that happens. We won't go into the details of that because the scheduler takes care of it for us, but it raises an important point. Calling a coroutine doesn't make anything happen directly. The scheduler needs to start it running before anything will happen, and the scheduler doesn't even know we called the coroutine until we use the coroutine object with await async IO.createTask or async IO.run. So the practicalities boil down to this. We can create coroutine functions by defining them using async def. Within coroutine functions, we can call other coroutine functions by using await to wait for them to complete. And await also lets us wait for other pending events, such as task completion, to occur. We can use async IO.createTask to launch new tasks, and async IO.run to launch our main task along with the async IO scheduler and main loop. We can have a huge number of tasks going at once in a single thread, especially if most of them are waiting for something to happen. Now we have some idea of the theory and practice of async IO and coroutines.